And why are they referred as universal gates? I told you that all three basic gates, that is NOT and OR, can be realized. Hello everyone, a very good afternoon guys, and welcome to Plutus IAS. Guys, today we are going to discuss a very interesting topic of physics optional for UPSC, and the topic is universal gates. Guys, universal gates are basically of two types. They are NAND and NOR gate. Okay. Now, this topic is actually the extension of logic gates. We are under semiconductor devices, and in semiconductor devices, we are doing logic gates. Logic gates are of three types, three basic types. I'm just going to give you a brief and precise introduction because we have done logic gates in detail in another video. This video is specifically about universal gates. So, NAND and NOR are universal gates, and three types of basic logic gates are: number one, NOT gate, number two, OR gate, and third is AND gate. And guys, these gates are mathematical sort of operations. Okay, there is a different set of algebra dedicated for these gates that is known as Boolean algebra. That we will discuss in some other video. Today, we are going to concentrate on NAND and NOR gate. Okay, so let's get started. First of all, why these gates are called as universal gates? So these gates are called as universal gates because we can realize all the three gates, all the three basic logic gates, that is NOT and OR, with the help of these two gates individually. That means with the help of NAND gate, we can design AND gate, we can design NOT gate, and also we can design NOT gate. Okay? And with the help of NOR gate, we can again design all three basic gates. Understood? So let's get started with NAND gate. So NAND. Guys, the name means, NAND means AND plus NOT. So if you combine AND gate and NOT gate, combination of AND gate plus NOT gate is going to give you NAND gate. So I'm going to draw the diagram for it. So this is my AND gate. It has got two inputs, right? And this is the output. Now I'm going to feed this output to the NOT gate, and this combination will give me NAND gate. Okay, let the inputs be A and B. Here I am obtaining, let's say, Y, and the output is the complement of Y, that is Y dash, and that's the output of NAND gate. Okay, so if I draw the symbol of NAND gate, so it's very simple. First you have to draw the NAND gate and then apply this circle to represent NOT gate. Okay. And let's say here the output is this Y bar, let's call it X. X is the output. Okay. So that's the symbol of your NAND gate. This is your NAND gate. And guys, these are the logic gates. You have to write these things in these letters in block. Okay, capital. Fine. Now let's move on. Let's talk about the truth table. Truth table of NAND gate. So see, we have got two inputs that we fed in the gate. So A and B are two inputs. Now, what's the scenario of writing the truth table? I have told in previous classes when we were discussing the basic logic gates Always write it in this format in which I am writing. See, 00011011. That's the format. Okay, this format is going to help you in solving various numericals and operations. Okay, so always write in this format. Now, what are we doing? We are doing AND of these two. AND means in mathematics, we call it multiplication. Here we call it AND. 0 will give you 0. 0 into 0 is 0. 0 into 1 is also 0. 1 into 0 is 0. 1 into 1 is fine. Now, and see guys, do not confuse AND operation with the multiplication. It is not multiplication. It is the operation of Boolean algebra. But so that you can relate with it, so that the concept becomes clear in your head, I am saying that you can synchronize AND with multiplication. Okay? But if something like this is written, you will call it A and B. You will not say A into B, being the student of physics. Fine. Now you have to take complement of this entire thing. Complement means just the reverse of it. So reverse of 0 is 1. Reverse of 0 is 1. Reverse of 0 is 1. Reverse of 1 is 0. That's your output of NAND gate. That's the truth table of NAND gate. Okay. Now guys, I have written this expression. If I open this expression, and in order to open this expression, we need to know few basic steps of Boolean algebra. We have discussed Boolean algebra in another video, but here, since we need it, I am going to mention it to you as well. So according to Boolean, suppose you have got the input A, okay, or let me say, we have got A 1, we have got 1, and you take complement of it, you will get 0. Complement of 0 will give you 1. Okay, just the opposite. Suppose A complement is written and you again do the complement of it, so you will get A. Fine. If A dot B is written and you do the complement of it, so what you will do, you will distribute this complement. So A complement. Now complement of dot becomes plus. Complement of AND is always OR. Plus sign represents OR in Boolean algebra. So dot becomes plus, that is plus B complement. Similarly, if you do A or B whole complement, you will get, again it will distribute itself, A complement dot B complement. Clear? These are the basic Boolean operations. Okay. So see guys, if you open or distribute the complement on this expression, what are you going to get? You are going to get A complement plus B complement. Okay. So let's do it. I'm going to erase it in truth table itself. Now see, A complement. Complement of 0 is 1, complement of 0 is 1, complement of 1 is 0, and again complement of 1 is 0. That's what A complement is. Now draw for B complement. Complement of 0 is 1, complement of 1 is 0, complement of 0 is again 1, and complement of 1 is 0. Now do the OR operation between them, A complement or B complement. Now see guys, the basic OR operation we know that we are talking about digital signals, and in digital signals there can be only two outputs, 1 or 0. 1 represents signal is present, 0 tells us signal is absent, right? For just like a switch, electric switch, you put the switch on, what happens? The fan starts rotating. You turn it off, fan stops. So electricity, when you turn it on, current flows. When you turn it off, current ceases to flow. Similarly, in digital algebra, either signal will be present or signal will be absent. One is the representation of the presence of signal and zero is the representation of the absence of signal. Fine. If you add it, so 1 plus 1, that means from both the ends you are getting the signal. So in output also you'll get a signal 1. 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 1. Now guys, you can match both of these columns. See, and you'll observe that A dot B whole complement and this thing, they are entirely same. Same result is obtained. That means the expression that we wrote, that A dot B whole complement will give us A complement plus B complement, is correct. That's the proof of it. Understood? Okay. So that's your NAND gate. Now let's talk about NOR gate. NOR operator or NOR gate. So again, NOR is equal to OR plus NOT. OR plus NOT is going to give you NOR. Okay. So pay attention. That's the symbol for OR gate. We have two inputs here. Right. That's the output. And if you feed this output to the NOT gate, now you will obtain your NOR gate. So see, I'm going to draw the symbol, direct symbol, by combining these two symbols for NOR gate. So if A and B are your inputs, so A or B whole complement is the NOR operator. This is your NOR gate. Please look at it. Right? See, that's what we have done in the previous situation as well. Combining AND and NOT. Here we have combined OR and NOT to get NOR. Okay. Now let's draw the truth table for this. So again, A and B are my inputs. How are we going to write? 0, 0, 0, 1, 1, 0, 1, 1. Fine. Then what were we doing? We were doing OR of it. Do the OR. OR is again just like AND was synchronous with mathematical operator multiplication. Similarly, OR is synchronous with mathematical operator addition. They are not same, right? But in order to make it understandable, we can say they are analogous. So 0 plus 0 is going to give you 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Signal is present. Now we have to do what? We have to take complement of this result. So complement of A plus B is going to give you complement of 0 is 1, complement of 1 is 0, here also 0, here also 0. That's the result that you get. Now guys, if you break down this result, I'm writing it here. So distribute the complement. A complement, complement of OR gives you AND. I've already told you. Right? So A complement and B complement. That's what you get from here. Fine. So now let's verify the result. So I'm going to draw the column of A complement. 0 will give you 1, 0 will give you 1, 1 will give you 0, again 1 will give you 0. For B complement, 0 gives 1, 1 gives 0, 0 gives 1, 1 gives 0. Now you have to do AND of these two. So A complement and B complement, 1 dot 1 is 1, 1 dot 0, 1 dot 0, 1 dot 0. Now again you can see these two results are same. That means our concept is correct. That's the verification. Understood? Okay, let's proceed, guys. Now, see, when I started with this topic, I said that NAND and NOR are known as universal gates. And why are they referred as universal gates? I told you that all three basic gates, that is NOT and OR, can be realized with the help of these gates. So let's realize all the gates with the help of these gates. Okay. Let's see. First, I am going to realize all the three gates with the help of NAND gate. And then I'm going to do the same for the NOR gate. Okay. So first let's realize NOT gate with the help of NAND. And pay attention, when I'm saying with the help of NAND, I mean I will be using only NAND gate. No other gate can be used. Okay. So NOT gate. Now the problem with us is that in NAND gate there are two inputs, but in NOT gate there is one input. So how to work? If you want to make NOT gate out of NAND gate, you have to convert the inputs into one. So how to do that? So that's the process. We can do it. We can supply the gate with one signal, and then we can multiply this one signal, multiplex the signal into two inputs. Okay. This is your NOT gate in the form of NAND. Okay. Now let's draw. So we have realized NOT gate with the help of NAND gate. Now let us realize AND gate with the help of NAND gate. So pay attention. It's very simple. Here you will get the output Y, right? And what is this output will be? It will be A dot B whole complement. Yes or no? We have already seen it. We will get AND of A and B and complement of it. That's what the output of NAND gate will be. Now feed this output. Feed this output to the NOT gate. But pay attention, you cannot feed it to the basic NOT gate because you only have to use NAND gate. So feed it to the NAND NOT. That means NOT operator with the help of NAND gate that we have just drawn. So now complement of this, complement of A dot B. So double complement of A dot B or A and B will give you A and B. Understood? Okay. Now let us draw OR gate with the help of NAND gate. That's interesting. Realization of OR with the help of NAND. So pay attention. This is a signal A. I am feeding it to the NOT drawn with the help of NAND. So I will get A dash here. This is B. Again feeding it to NOT drawn with the help of NAND. And now I am going to feed these two inputs, that is A bar and B bar, to my NAND operator. So what will I get? Pay attention. A complement dot B complement and whole complement. Pay attention. Now distribute this whole complement. So what will you get? A double complement complement of dot gives you plus, and B double complement. Double complement will cancel out, so you'll get A plus B. That's the output. So what we obtained? We obtained OR with the help of NAND gate. Understood? Okay, guys. Now, similarly, we can now see, guys. You can also draw the truth table to realize it. If you have any problem, let me know. I will draw the truth table. But I hope it is clear. I have simplified it to make you understand that how it is operating. Fine. Now, if we talk about NOR operator, now I am going to realize all the three basic gates with the help of NOR operator. Number one is NOT gate. So again, it is very simple. I hope you can do it on your own now. This is the symbol of NOT gate through NOR gate. Fine. A is the input, then A complement is the output. Next, let's draw OR gate with the help of NOR gate. Again, it is very simple. So this is my NOR. A, B. So what will happen here? A plus B whole complement. Yeah, that's the result of NOR operator. Now I am going to feed this input to the NOT operator designed with the help of NOR operator. So pay attention. A plus B whole complement whole complement. So these double complement will cancel out and you will get A plus B. That is A or B. Clear? So that's the realization of OR gate with the help of NOR gate. Now guys, let us realize AND gate with the help of OR gate. With the help of NOR gate. So let's say here we have got signal A. Here you'll get A bar. If you have signal B here, feeding it, you'll get B bar or B complement here. Feed these two signals to your NOR. Whole complement. So pay attention, double complement A plus, again double complement, and complement of plus will give you dot, again double complement of B will give you B. So A dot B, that's what we wanted to realize. And operation means A dot B if A and B are inputs. So guys, we saw that with the help of NAND and NOR, we can realize all three basic gates. That's why these gates are known as universal gates. I hope you understood and enjoyed today's lecture. Thank you. I'll see you in the next video. Bye-bye. Take care.